So I want to now turn to looking at energy, and so to do that I need the velocity equation, which just came from our derivative, so that became a minus sign, and we got an omega as well from our chain rule, so minus a omega sine omega t, and so from that I can say my kinetic energy would be 1/2 mv squared, so that would be 1/2 m a squared omega squared sine squared omega t, so that would be my kinetic energy term. My potential energy for a spring is 1/2 kx squared, where k is my spring constant, and so if I plug that in I get a 1/2 k. Now I'm going to square the x, so that would be an a squared cosine squared omega t, and that's what's being plotted here. I've got potential energy and kinetic energy, but notice when I add these together, k plus potential, so kinetic plus potential energy, you can kind of guess it looks like when this is high, potential energy is high, kinetic energy is low, and they add together to give me a constant value, but you can actually see it mathematically. So we've got 1/2 m a squared omega squared sine squared omega t plus 1/2 k a squared cosine squared omega t, and now we can get our relationship back from the previous one that said omega squared, I'm pulling from here, omega squared equals k over m. So omega squared equals k over m. I'm going to just substitute that in there, and that's going to give me E is equal to 1/2 m a squared k over m. Okay, so the m's go away. Sine squared omega t plus 1/2 k a squared cosine squared omega t, and notice both of these terms have a 1/2 ka squared, so the energy, so I'm going to factor that out, so I'm going to have 1/2 ka squared times sine squared omega t plus cosine squared omega t. And hopefully you remember that sine squared plus cosine squared is just 1, so that whole thing is 1. And so, of course, my total energy is just 1/2 ka squared. So if I think about this, when I take my spring and I stretch it, so there's the x equals 0, and this is my stretched amplitude, amplitude being the value, the peak value for, right, that would be stretching it, so this would be A, that would be the peak value if I do x versus t. Then if I stretch it, then my maximum energy would be at this stretched point, which would be all potential energy, right? So this is all potential energy, so it shouldn't surprise you that that's 1/2 ka squared at that point, because we've got 0 kinetic energy there, and when we go into the center, it's all kinetic energy, which we can write certainly as this, or the kinetic energy, the maximum kinetic energy here. If I look at this equation right up here, Ke max is when sine squared is equal to 1, because that's the biggest sine can be is when it's equal to 1. Sorry, I was writing under where my picture was, but K max is when we have this equal to 1, or the maximum kinetic energy is 1/2 m a squared omega squared, which is of course equal to 1/2 ka squared, because m times omega squared is our k value. So this all works, and it's nice and consistent, which I think is very satisfying. What that says is that our total energy, if we want to add that up, is just a constant value. This would be my E total, right, for this particular setup, where at this halfway point, right, this looks like it's 1, so my total, well, it's slightly less than 1, so my total is slightly under 2. joules of energy. So I've got a constant total energy as it oscillates back and forth, and this oscillation of each of these, one of them is a sine squared term and one is a cosine squared term.